We'll be discussing Lab 1, where we looked at charge tape. The purpose of this lab was to carry out an experiment by charging a piece of tape and observing the repulsion towards another piece of tape. This is shown on the figure to the right. We will then use a computational program to find the magnitude of the electric force between two positively charged pieces of tape. The magnitude of the charge of the tape will also be found. We found the magnitude of the electric force to be 1.962 e to the negative 3 newtons. We found the magnitude of the electric charge to be 7.47 e to the negative 9 coulombs. The physics principles we used are stated here. We know that in static equilibrium, F net is equal to 0. In our case, we found that there were two forces, gravitational and electric. The force of gravity is 0, negative mg, 0. Because our system is in static equilibrium, we know that Fg plus Fe will equal 0. So we know the electric force will be the negative of the gravitational force. We also use the electric field equation E equals kq over r squared, and that is the magnitude of the electric field. We also use the electric force equation, electric force equals E times q. The previous physical principles were needed to find the magnitude of the electric force and electric charge. Because our system, the tape, was in static equilibrium, because they were stationary, we know that F net equals 0. Because there are only two forces acting on the system, electric pointing up and gravitational pointing down, we know that the electric force will be equal and opposite to the gravitational force, which we can calculate knowing the mass of the tape. Once we know the electric force, we can set it equal to the electric field equation and solve for Q, the charge of the tape. The initial conditions of my code were that the tape length was 0.2 meters, which meant the tape mass was 0.0002 kilograms. The separation distance between the two pieces of tape was 0.016 meters. K is equal to 9e9, E 1.6 e to the negative 19, and G 9.8. The assumptions I used were that the tape was treated as a point charge with charge accumulated at its center. Both pieces of tape have equal charges with equal charge distribution, and forces other than gravity and electric were ignored. My code worked to first set the initial conditions and then setting the relative positions of the pieces of tape modeled as points. After this, the force of gravity on our tape that was the system was found using the Fg equation. Because we know the system is in equilibrium, the gravitational force must be equal and opposite to the electric force, so F net will equal 0. Using this principle, the electric force was found. The charge of one piece of tape was found by using the electric field and electric force equations to solve for Q. Finally, arrows were added to the modeled point particles to visualize the two forces acting on the system. Here are the results my code modeled. The system was the tape on top, which is in purple, and the surroundings were the tape on the bottom in blue and the earth. The code output the forces acting on the system. The gravitational force is the green arrow and the electric force is the blue arrow. The numbers output are the magnitude of the force of gravity and the magnitude of the force of electricity, which was 1.962 e to the negative 3 newtons, and the magnitude of the electric charge of the tape, which was 7.47 e to the negative 9 coulombs. Because of the assumptions we made, this model output will not be exactly the same as observational data. Therefore, the charge we gleaned from our code is probably not 100% accurate. Some errors that could have caused this is that there is air resistance acting on the system that we did not account for, and the pieces of tape do not act like point charges in reality, so this was an oversimplification. If the electrons had a positive charge and protons had a negative charge, the observations we made with our tapes would remain the same, and the charge's magnitudes would remain the same as well. The sign of the charge of the tapes would change. Electron deficiency in this case would mean the tape would be negatively charged instead of positively charged like in the original experiment. It was important to handle the charged tape as little as possible in this experiment because contact with other neutral objects would allow the electron deficient tape to acquire electrons. This would return the charged tape to a more neutral state, which would decrease its ability to effectively repel the other piece of tape.